In Chapter 5, we talked about equilibrium of individual rigid bodies. We now turn our attention to assemblies of rigid bodies. One of the simpler assemblies we'll encounter is an assembly of two-force members. You might recall from Chapter 5 that a two-force member is particularly simple in that it transmits a single force whose line of action passes through the pin connections at the ends of the two-force member. In this case, every member of the assembly is already known to be in equilibrium, but we don't know yet the size of the force carried by each member. We will refer to assemblies of two-force members as trusses, and we will examine different methods for determining how much force each member carries. These methods of examination are called method of joints and method of sections. Our initial examination will focus on 2D trusses. Once we become comfortable with applying these methods in 2D, we'll extend the treatment to 3D. There really isn't anything different about applying these methods to 3D problems, but the 3D nature makes those problems more complicated. A more general assembly of rigid bodies permits the members of the assembly to experience a much greater variety of loads than just the simple force transmission of the two-force member. A general assembly may contain one or more two-force members, but many of its members may transmit force couples or multiple forces. Such an assembly that is intended to be stationary is referred to as a frame. Such an assembly that is intended to move and perform some function is referred to as a machine. Even though machines are intended to move, our interest is confined to temporary configurations where we can use the equations of static equilibrium to determine loads transmitted by the machines. A member that has pinned ends and no ability to react moments, and that just transmits a force between those ends is a two-force member, and it is already in equilibrium. If the weight of the member is significant, then there is an intermediate force between the pinned ends, and it can't be treated as such. To treat it as a two-force member, we either have to apportion its weight to its ends using equivalent force system principles, or ignore its weight. In many applications, there are structural elements that have a substantial weight, but that weight is insignificant compared to the loads transmitted between the ends. Hydraulic cylinders, especially on earth-moving equipment, are examples of heavy structural elements whose weight is negligible compared to the force transmitted by the cylinder. When you see a pneumatic or hydraulic cylinder in a machine problem, you should immediately think, this is a two-force member. Some of the details of truss construction also don't strictly follow our two-force member requirements, but we're going to approximate the structure as an assembly of two-force members anyway. This slide summarizes some of the features of two-force members. We can elaborate on some of these bullet points as follows. The first bullet point reads that all members must be connected to one another by frictionless pins, and the locations of these are called joints. The key phrase here is connected by frictionless pins. If a pin is frictional, moments develop as members connected at the pin rotate with respect to one another. The presence of a moment voids the ability to treat the member as a two-force member, hence the connection must be frictionless. Our second bullet says that each member may have no more than two joints. If there were more than two joints, then at least one joint would represent an intermediate point between the ends, where forces from adjoining members would be applied, and the assumptions inherent in a two-force member treatment would again be voided. Our third bullet says that forces may be applied at joints only. This is another variation of the requirement that there be no intermediate loads between the ends. Finally, our last bullet says that the weight of individual members must be negligible. Again, this is yet another variation of the requirement that there be no intermediate loads between the ends. In fact, the last three bullets here are all variations of the same requirement. The second bullet imposes no intermediate internal forces, the third bullet imposes no intermediate external forces, and the last bullet imposes no intermediate external forces due specifically to weight. The important point, however, is that a two-force member only transmits force along a line of action connecting its two pinned ends. A common application of truss analysis is bridges, and we see a perspective view of one such truss here. The actual connections between members in bridges are far more rigid than is implied by our treatment of trusses as assemblies of two-force members. Gusset plates can have hundreds of rivets in a single connection. This means the actual connections between members have the ability to react moments, which is in violation of our treatment of the assembly as a set of two-force members. Nevertheless, the actual axial loads carried by members of the assembly are well approximated by treating the assembly as a set of two force members, and we will use that approximation independent of the actual connections between members. To emphasize our point, consider these two details of a roof and bridge truss. In the roof truss, it's not uncommon to have a single continuous span that goes all the way across the bottom of the truss. This would violate our two-force member treatment in that there would be multiple joints all the way across the truss bottom. Instead of treating the bottom member as a single continuous member, we break it up into a series of two-force members, each of which is continuous between joints. Here, for instance, instead of considering our actual joint this way, what we might do is consider these coming together this way. So here's our continuous span along the bottom. We're going to approximate this as though it's got a pinned joint here, even though we can see that the actual member here is part of a continuous span. By the same token, over here on this bridge truss, right here at A, I'll draw a dot, and this will be one part. This will be one joint here. I'll make this a bigger dot to emphasize the pin connection here. We obviously have a pin connection here, but we would approximate these things this way, even though the actual connection between those members is more rigid than a pin. We're going to treat them as a pin anyway. As mentioned earlier, each two-force member is already in equilibrium, but we don't know yet how much force each member carries. The primary objective of truss analysis is to determine the axial load carried by each member and whether it is in tension or compression. We do this by imposing equilibrium on different parts of the structure. We can impose equilibrium on the whole structure, in which case we're solving for reactions. We can impose equilibrium on the smallest unit of the structure, a joint, or we can impose equilibrium on a subset of the structure. In the former case, we use an approach called the method of joints, and in the latter case, we use an approach called the method of sections. In all cases, though, what we're doing is imposing equilibrium. It is often useful to begin by imposing equilibrium on the whole structure. We can do this if the 2D structure has no more than 3 unknown support reactions and is statically determinate. Our first example will fall into this category. It is not always the case, though, that the structure lends itself to this first step, and we may have to begin by examining a joint. There is one critically important distinction between imposing equilibrium on a joint and imposing equilibrium on part or all of the whole structure. Each joint represents a point of concurrency where the lines of action of the participating members intersect. For this reason, a joint is already in moment equilibrium and is treated as a particle. For each joint, then, we can only write 2 independent equilibrium equations in a 2D problem, or 3 in a 3D problem. An important part of the method of joints is identifying a joint sequence that allows us to move from one joint to another, obtaining information about member forces as we go. Consider this first truss example, an assembly of 7 two-force members connected at 5 joints. We want to determine the force in each member. We can see from this structure that it is pin supported at A and roller supported at D, so a free body diagram of the whole structure is statically determinate. We begin by isolating the whole structure, providing the free body diagram shown in the next slide. So here we'll draw a closed path around this that goes through the joint here at A, and then the joint, and then the reaction here at D, and essentially captures everything inside here. And then our free body diagram based on that isolating surface looks like what we have here on the upper right. Note that there is no reason to draw the internal components of the structure, that is, the individual truss members, because they're internal to our enveloping surface. The reactions at A and D depend on the points of application of external loads, so we only need a crude outline of the structure and the ability to see the lines of action of those loads. Applying force and moment equilibrium in the conventional way permits us to find the reactions. In this case, AX is minus 1 kilonewton, AY is 1.75 kilonewtons, and DY is 3.25 kilonewtons. Now before we go forward, let's actually go back to our truss structure here in slide 7 and consider the free body diagrams of individual joints. So we've already determined now the reactions at A and D. We'll go ahead and isolate each individual joint now. We're isolating joint A, B, C, D, and E. Two things to note here: if we're isolating a joint that also coincides with a support, as at A or D, then the support reactions are also applied to those joints. Second, it usually isn't obvious by inspection whether a member is in tension or compression. Although your physical intuition may grow as you solve an increasing number of problems, as a novice, you're probably not going to be able to tell what is in compression and what is in tension, and that's okay. One approach is to draw all the members as though they're in tension, even though they won't be, and then interpret positive numerical values as tensile and negative numerical values as compressive. You can always think of a negative tension as a compression. If we think about, for instance, here member AB, suppose we're just isolating this here. Now here's our member AB here, and if this is in tension, then it's by definition of being in tension, it's being pulled on either side here like this, which means that if we think about what's happening at, let's say, joint A, what I would have here, this force at the location here on the left of AB, at this location here, we're going to have an equal and opposite force that's exerted on joint A. So if AB is in tension, it's going to exert a force on the joint inside A. As we can see by examining member AB, for instance, a member in tension exerts equal and opposite forces on its joints, so that tensile members exert forces on the joint that tend to pull it apart. In contrast, compressive members exert forces that tend to push it together. In our subsequent free body diagrams, all members are shown as tensile, and we'll let the algebra and subsequent numerical values tell us whether or not they actually are in tension. So now we'll proceed to our free body diagrams of the joints. And again, forces exerted on the joints imply members are all in tension. All the forces we know, whether external forces or reaction forces, are shown in red. The member forces we're sinking are shown in pink. The question now becomes how to proceed. Here it helps to remember that particle equilibrium of each joint permits us to solve for at most two unknowns at each joint. There are only two joints where we have two unknowns, A and D. Either place is an equally good place to start, and the solution shown here represents one of several acceptable joint sequences for finding the solution. Before we get into the solution details, let's define an acceptable joint sequence beginning from A. Once we solve for member forces FAC and FAB, we can proceed to joint C. With FAC now known, we can subsequently solve for FBC and FCE. With FAB from joint A and FBC from joint C now known, we can proceed to joint B and solve for FBE and FBD. With FCE from joint C and FBE from joint B now known, we can then proceed to joint E and solve for FDE. At this point, we will have solved for all member forces. You may notice something about this process that raises a flag. Beginning from A, we have two equations and two unknowns. Proceeding to C and using the result from A, we have two equations and two unknowns. Proceeding to B and using the results from A and C, we have two equations and two unknowns. Proceeding to E and using the results from A and B, we have two equations and one unknown. In fact, we could then proceed to D, where using the results from B and E, we have two equations and no unknowns. Is there an inconsistency here? There isn't, because we've imposed equilibrium on so many different parts of the structure, in whole and in part, that eventually we begin to overlap our imposition of equilibrium. This is still useful because we can use our previously obtained results to check the accuracy of our calculations. Vertical equilibrium of joint E provides FDE, and horizontal equilibrium of joint E should be identically satisfied. By the same token, we should find both horizontal and vertical equilibrium of joint D to be identically satisfied if we choose to go one step further and impose equilibrium there. In fact, we can see by beginning from joint D that member FDE must equal minus 3.25 kilonewtons, that is, DE carries a compressive load of 3.25 kilonewtons, and that member BD carries no load. So if we choose to begin from joint A and proceed to C, then B, then E, and then D, we have checks on the accuracy of our calculations by the time we get to D. Moving to slide 10, we see the equations for a different joint sequence, A to C to E to D. We have skipped joint B, but it is not necessary to examine it to get all the information we need. If desired, we could check the accuracy of our results by writing the equilibrium equations at joint B, substituting in all values, and verifying that horizontal and vertical equilibrium are identically satisfied. Note that the numerical results tell us that members AB and BE are in tension. They have positive values. Members AC, CE, and BC are in compression. They have negative values. And one member, BD, carries no load. Many of the preceding remarks are summarized here. A more quantitative description of our equilibrium redundancy is given at the bottom of this slide. In the joint sequence I described earlier, we had 3 extra equations, 1 for joint E and 2 for joint D. But this exactly matches the number of equilibrium equations we used to impose equilibrium on the whole structure before we began examining the individual joints. So this is entirely consistent with the process that we followed.